Okay, gang, let's begin. We're going to talk about wiggles and jiggles. What's the difference? What's a wiggle in time called? Does anyone know? A wiggle in time. Begin with a V. Vibration. And what's a wiggle in time through space called? Begin with a W. A wave. So we're going to talk about wiggles in time and wiggles in space. Vibrations and waves. We talk about vibrations, something maybe bobbing up and down, or a pendulum swinging back and forth, or something that occurs and recurs. I could take my chalk on the board and I could vibrate it up and down. I'm vibrating a little bit too, okay? This is a vibration, all right? Now, how frequently I go to and fro has to do with frequency. We talk about frequency with that letter F. Here's a low frequency. Want to see a high frequency? This is common sense stuff. Yeah? Isn't it? Guess what a very high frequency is? How many say, gee, I don't know what he's going to... Come on, you guys know. What's a very high frequency? Like that, yeah? Okay. But when that high frequency is propagated through space, watch. It traces out what we call a... It's really a sine curve, but a representation of a wave, okay? Now we're going to go through some definitions, gang. There's frequency dragged out. The dotted line is my equilibrium point. I'm going to vibrate above the equilibrium and below. And I go just as far above as just as far as below. I call this particular distance here, by the way, let's label these things. What do you call the maximum displacement of a wave? Begin with an A. Amplitude. You didn't even need the rest part. The other class, I have to say, begins with an A, ends with a tude. And they really go bonkers, okay. Amplitude, then they get it, okay. We see it's amplitude. So we put amplitude A. A lot of people think amplitude is from here to here. No. That's the peak to peak distance. The peak of the wave, the other peak. Amplitude is the maximum displacement from the equilibrium position, yeah? Right. These are just definitions. These are definitions so we can talk about sound meaningfully, and also so we can talk about light meaningfully, because they're both forms of waves, yeah? Okay. We call this distance from here to here a wavelength. Wavelength L. Now we could put a L here. But does that look kind of exotic? L? Doesn't it look sort of bland? Wouldn't it be nice to jazz it up a little bit and use maybe a Greek letter L? Yeah? We can do a Greek letter. Anyone know what a Greek letter L is called? No, nobody knows. Yeah, anyone? Any Greek scholars? No, not alpha.
Lambda?
Ah, lambda. Lambda. That's right. And lambda. Watch. That's not so exotic, is it? Your parents see that you're doing like this. They say, oh, it's an L. I know the alphabet. But what if your parents look down and they see you doing this? Ooh, heavy, honey, heavy. You be learning that stuff? And you say, I know that stuff, okay? That's just the Greek letter L stands for wavelength. You see it all through wave nomenclature. So you ought to know what it means. That's just the Greek letter L, length, the length of a wave. So the length of a wave is from peak to peak, or it's from here to here. This would be lambda as well. Some people get mixed up, and they say, oh, it's from here to here. But no, this part of the wave is going down. It's going up. You got to wait till it gets to a complete cycle. Boom, down again. See? Lambda is the wavelength that a wave will travel in a complete cycle. A two, and two again. To, fro, to. See what I'm saying? So that's your wavelength. And that wavelength, of course, could be, you can see it anywhere in there. Usually peak to peak, or oftentimes from here to here is shown. This is a wave starts, and here's where it ends. So this is a wavelength. Wavelength, wavelength. Kind of easy stuff. So when you talk about the wavelength of a wave, when I say wavelength of a wave, we'll all be talking about the same thing. Yeah? Okay. There's another thing with a vibration too. There's something vibrating here. Okay. Now, the vibration has a frequency. What do you suppose the frequency is, gang? What do you mean what the frequency is? It's the vibration, what you said. What's the value? What's the numerical value of the frequency? Well, the frequency would be how many cycles per second. Let's start here.
per second.
What do you get, Lee?
About 1 per second.
1 point what?
1 per second.
Well, let's just say 1 per second. If it swings back and forth 1 time per second, then its vibration frequency is 1 vibration per second. Ain't that neat? Or we could say 1 cycle per second. Got that? Or we could say 1 avis. No, wait. 1 hertz. Okay? 1 hertz is a shortcut name for 1 vibration per second. You got it? Now let's suppose I swing it back and forth 2 times per second. Guess how many hertz I'm vibrating now?
2.
You give me the T. Too easy? 2. It's easy, huh? Try this one. Try this one. Let's suppose I vibrate it back and forth 7 times a second. Yeah, all right. 7.9 times per second. How many hertz? 8. Not 8. No. Almost 8. Almost 8. Let's suppose we get real nitty-picky now. 7.9 vibrations per second. How many hertz is that? 7.9 hertz. You see what I'm saying? Okay. Now let's get to another idea. Not what the frequency of vibration is, but let's talk about the time during which 1 cycle occurs. This one is 1 vibe per second, 1 hertz. How long does it take in seconds to undergo 1 complete cycle? Begin with a W. 1. Okay. Let's suppose I swing it at twice the frequency. How long will it take for 1 cycle? Not everybody be saying, but most people be saying. Check the neighbor and see if the neighbor knows what the time is for 1 complete cycle when it's shook at 2 hertz. What's the answer, gang? I'm going to say a half. All right. Let's suppose I had told you I shake it back and forth 7 times per second. What's the frequency?
7.
Be careful, be careful, be careful. Do you see what happened? You all expected me to ask what's the time. I'm going to call that time, begin with a P. Period. And you're all expecting me to ask you that. Be careful in school, because they didn't ask you that. I asked you a different question. What's the frequency?
7.
Next Friday when we take our exam, you start to read the question. Oh, I know what the answer to this is even before you have the question. Be careful, the question might be different than what you think it's going to be. So again, if I shake this back and forth 7 times per second, what's the frequency? 7 hertz. Now, what's the period? 1/7. So it turns out there's a relationship between frequency and period. Frequency F is proportional to 1 over the period. In fact, it happens to be exactly equal to 1 over the period if the frequency is in seconds, or in hertz, and the time is in seconds. And you can just say they're reciprocals. So you just turn it upside down. In your homes, the electricity that powers your appliances at 60 hertz. That means the electricity is alternating back and forth. Guess how many times every second? 60 times. What's the period? What's the time it takes for 1 to and fro swing? 1/60th of a second. All you do is reciprocate the frequency, and you got the period. Or reciprocate the period, whip, boom, you got the frequency. Do you see that? Okay. So those are important ideas. Another important idea when we talk about waves is wave speed. How fast the waves travel. And how fast anything travels is simply the ratio of how far compared to how long. So if I talk about wave speed, it's simply equal to, is this true what I'm going to say?
No.
What's wrong? Is that true? Wave speed, distance over time? Gang, any kind of speed is the ratio of how far you go compared to how long a time it takes, right? Well, let's talk about this wave that we generated that was coming running down the blackboard here. Coming down the blackboard, okay? The distance, let's take some distance, divide by the time, I got it. Let's take a distance of 1 wavelength.
divided by 1.
That's the distance to go from here to here, or from here to here, or from here to here. If I know the time that goes by during the time a wave goes one wavelength, then I can put that in here, and I can have the wave speed. If I were interested in things like that, and we kind of are, aren't we? And what is the time it takes for a wave to go one whole cycle? What do we call that time? Begins with a P.
Period.
Period. Okay? And so one over here, we can say wavelength over the period of the wave will give you the speed of the wave. But the period of the wave can be rewritten. 1 over the frequency. And those of you who are a little bit into mathematics know that this is the equivalent to. Let me write it this way. And so we have a relationship for the speed of any kind of waves, gang. And it simply is the velocity of the wave, the velocity over the speed is the magnitude of velocity. That velocity of the wave is simply going to be equal to the frequency of the wave multiplied by its wavelength. Later on, we'll talk about the speed of light. And the speed of light will be equal to the frequency of light multiplied by its wavelength. So if you know the wavelength of light, you can calculate the frequency if you know the speed. And turns out light speed will always be the same. Do you know how fast light goes, gang? It goes just as fast as a radio wave goes. It goes just as fast as an infrared wave goes, as ultraviolet wave, gamma ray, all of the electromagnetic waves. Guess what we're going to be talking about later in the course, gang? Electromagnetic waves. They all have the same speed. That's 300,000 kilometers per second. In fact, for light, we say it's a constant, so we say C. C for constant. That's 300,000 kilometers per second. And that's equal to the frequency of the wave multiplied by its wavelength. Questions?
What is the label for the
Say again?
the label of each? It has to be a certain thing, right? Like for your distance, shouldn't that be a labeled in meters or something?
Oh, yeah. If this is in meters and this is in seconds, then I get meters per second. And I'll have my speed in meters per second. It turns out for a light wave, you go 300,000 kilometers in 1 second. So you'd have distance in meters or kilometers, or micrometers or miles, yeah? And t in some unit of time. Could be like days, huh? It could be hours. We talk about miles per hour, meters per second, all those things. But a unit of distance, a unit of time.
So will the formula work for any unit?
You might have to fudge around your units. Let's suppose your frequency is in cycles per second, okay? And you want the speed in miles per hour. Then you've got to change seconds to hours, and you do that kind of thing in a lot of courses. You have to convert from one to another. But if you have this, for example, in cycles per second, and this in meters, then the speed will be in meters per second. If this is cycles per second or hertz, and this is in like millimeters, then your speed will be in millimeters per second. And it kind of makes sense. But this is the relationship, that these are tied together like that, which is kind of nice. You know? In general, we just say speed. The C was for the speed of light.
On the 300,000 kilometers a second, is that a convention for the convenience of math, or is that the actual speed?
It's almost that actual speed. It's 299, and I can't remember the numbers. But it's very, very close to 300,000 kilometers per second. Yeah, it's not. That's rounded off. And you'll find that later on in the book, what the presently accepted value is. It's close to that. Did you ever wonder about a radio wave, how long maybe the wavelengths might be? The wavelength we saw over here is about less than a meter. There are radio waves in this room, gang. You be knowing that. How long are these waves? Are they tiny, tiny, or are they big, big? Well, we can find out. We can find out. Because if speed is frequency times wavelength, and the speed of a radio wave, does anyone here know what the speed of a radio signal is that come from the radio antennas downtown? Anyone here know what the speed of those signals are? I'll bet there's people in this room that know. In fact, I'll bet that most of the people in this room know, and they say, wait a minute, isn't that the speed of light? Didn't he say the speed of light? How many people saying, yeah, I think it's the speed of light? No, the speed of light's for light. This is a radio, honey. It's different. No, it's not different. It's just a low frequency. We're going to learn later on just a low frequency light wave. And they all have the same speed. So the speed, 300,000 kilometers per second equals the frequency of the wave times the wavelength. Give me your favorite radio station. What's the call letters?
KCCN.
KCCNN. What's the number for KCCN? What is it?
AM.
What, 1420?
AM.
Is it 1420? Let's see how long those waves are. The frequency, gang, is guess what? 1420. Can we round it off to 1400? I can't do twos.
No, it's gonna
Huh? Oh, that's 1400 kilocycles, right? Kilocycles. That's another 1,000. That's the frequency. And now we got to get the wavelength. Well, we get this multiplied by this will give this. Do you know there are people who know how to find this, knowing the other two? There be. They're called engineers and science types and physics types. In fact, they're us types, aren't they? What's the wavelength, gang? Let's go. Watch this. 1, 2, 3, 4, 5. Now it's 3/14. Okay, so wavelength equals 3/14 of a what? Kilometer. Okay? That's like 3,000 meters divided by 14. Why did you pick a 4, man? I mean, how many times does 14 go into 3,000? Does anyone have a calculator?
214.28571.
214 meters long. Is that surprising to you? That's like 2 football fields and then some. So the wavelength of your favorite radio station is more than 2 football fields long. Radio waves are long or short compared to light waves, gang. We'll do the same thing for light waves later on and find out it's a smidge. The zeros go the other way. Yay. Anyway, that's how you find the wavelength of something. I can show you the slinky here. Someone grab the end of this for an A in the course. Right over here. Now I'm going to take this wave and I'm going to shake it back and forth along the direction like this. Well, I'm going to get it stretched a little bit more. If I vibrate it like this, can you guys see that the vibrations are along the direction of travel? We have a name for that kind of wave. Of course, there's 2 kinds of waves we're going to distinguish. Longitudinal and transverse. What kind of wave do you suppose it is that vibrates along? Longitudinal and transverse. Along the direction of wave travel. How many say, oh, it's probably a trick. It'll be transverse because it seems like common sense to say longitudinal, right? What's the answer, gang? Longitudinal. How about if I vibrate it transverse to the direction of wave travel? Just like the kind of wave I have here. What kind of wave is that, gang? That's a transverse wave. And both those waves have a wavelength, frequency, period, wave speed, the whole shebang. All the characteristics of waves. Thank you, David. Ted's got some nice things here to play with, gang. Ted Bradstrom, our TA.
Okay, waves are all part of the game, and we're not loud enough. There we go. Do we see waves or do we see waves?
Yes.
Okay, we can also have voice waves, and they look much more interesting. We go, ah. And you can get complicated waveforms and nice, easy waveforms. You can make whistles. Yeah, well done.
You know that everyone has their own pattern, like your own fingerprints.
Hold on. Where are you going? Go away on me.
Hey, there we go. Stood still.
Hello. Testing. Ah, hello? Hello.
Maybe
There we
that's
are
good.
again. Hello. 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 Loads of fun. Okay, I admit I'm a great singer. You want to do beats?
Maybe we could show the idea of interference.
Okay. What we want to do here is
First of all, I had to show the students that this happens because a lot of people don't believe it. Do you guys know that one wave can interfere with another in an interesting way sometime? Let me show you what I mean for water waves. Water wave. Let's suppose I take another water wave and add it right on top, and the other wave is exactly the same frequency, same wavelength, same everything, okay? Watch this. When those combine together, guess what I get? Is that remarkable? That's not so remarkable. You kind of expect that. But you want me to show you something that is remarkable? You like to see it?
Oh.
Take this. Let's suppose I add another wave, but I start out of step. By the way, physics types never say out of step when they talk about waves. They use a little more pizzazz. Begin with an F. Out of what? Out of phase. And if those two waves are completely out of phase, guess what the combination produces? Nothing. Nothing. That means if I take these two tuning forks, which are tuned for the same frequency, I know that because they just resonated, and I strike one, and then I strike the other, just out of phase, guess what you're going to hear? Guess. Begin with N. Nothing. Would you like to hear one sound destroy the other? I can do this. Listen to this now. Okay, I'm usually good at this. It requires that I hit this one, and as it's going, with my judgment, hit this one right when this one's sending out a high pulse. This one will send out like a rarefaction. Did you read about the difference between compressions and rarefactions? You know, when I strike this thing, the waves, boom, boom, compressed air comes out, and compressed air, compressed air, compressed air, followed by decompressed air. Watch this. Now, listen. Hear that? Did you hear the absence of sound? Did you hear? Was that neat? I never do it more than once because I don't want to trust my luck. But you get the idea. But I'll tell you what. Let me get these things so they're a little bit different in frequency. And strike them both at the same time. Can you hear the throbbing? That is a result of interference, and the phenomenon is called this phenomenon of pulsating, two sounds pulsating in and out of phase is called, by the way, scholars, beats. All right, I thought you guys were putting me on there for a while. And that's beats. Ted, can we show beats up here?
hopefully show beats.
So you can see as well as hear what's going on. You can see the waveform. Isn't that nice? We certainly hear the waveforms, but now we can see them. So this device, called an oscilloscope, beautiful, allows us to see the shape of waves. Very, very nice. Where it's extra loud, a compression from one fork and a compression from the other have reached your ear. And where it's very low, a compression is matched by a rarefaction. And one fills in the other and makes it like null. Isn't that nice? Question, Paul.
Can you explain why those laser discs are supposed to have a better sound quality than a tape?
Those laser discs amaze me. Let me tell you what a laser disc does. You saw Ted sang in here and showed you a particular wave. Well, when Ted did that, Ted maybe made a wave like that. Now what I want to do is I want to record that wave and give it back to you. The old way of doing it was just to have Ted speak into a microphone, and when he spoke into the microphone, the little crystal would start to vibrate too. And the crystal vibrates like that. The electrons get squeezed up here and spread out here, so they just pass through the wire. And as the crystal vibrates, the little electrons will vibrate too, just in rhythm, by the way, because the electrons have hardly any inertia. And so you get an electrical signal, and that would be brought over to a little needle that'd be riding on a wax disc, and the needle would vibrate the same way, and those vibrations would be caught up in the wax disc, and you play it back, and you whoop, you get the same tone. That's the old way of doing it. Well, now they say you want the signal just to go from here, at this point here, you want it to go that high, here, this high, here, this high, this high, this high, this high. Why don't we just measure the distance from here to here and send that through? And that's what a laser disc does. When it gets to this point here, it just tells you what the amplitude of the wave is. And it does that with little zeros and dots. And says, all right, here. Boom. Short time later, it's up to here, and it sends you what the amplitude is there. Zeros and dots, a number. And now it's up to here, and then to here, and to here. So all your laser disc is doing is counting off the amplitude as it goes along and tracing out the wave. It's amazing. That's what it does. And there's nothing to wear out now. Because the old record would finally get a little get a little worn out. But all the laser disc does is it tells you how high the wave is at different points. Period. And then with that information, then you play it back and you get it. Another interesting difference between a laser disc and a regular disc, the record player. By the way, these records, some of you guys still have some records at home, right? Hang on to them. They are collector's items. You're going to show them to your kids. And your kids are going to say, wow, were you around when they had those things? Say, I used to dance to those things, honey, okay? Yeah, they're going to go out. Hang on, you won't see them very much longer. But a laser disc doesn't travel at the same speed. I didn't know that until recently. You know, a regular record travels at the same RPMs, yeah? So out in the end, it's going faster, isn't that true? But on a laser disc, it travels at the same linear speed, but different RPMs. When you're in at the center, that's where it begins, by the way. A laser disc begins at the center and works out. Another upside down again. And when it's the center, that thing is spinning faster. And when it gets out here, it's spinning slower, so that the message goes under the laser beam at the same speed no matter where you are. You don't get that on a phonograph record that has a constant RPM. On the edge of the phonograph record, that thing is racing under the needle. That's where your best fidelity is, out there. And as you get closer in, now that part there, that is going slower. Isn't that true? You guys know it's slow. The inside of the wheel goes like slow, and the outside of the wheel keep up going faster. Laser discs just the opposite. Laser discs are amazing. So many things are, yeah? So when you get your laser discs, you say, well, this is as far as they're going to go. And they'll never have anything more than this, right? And down the road, they say, oh, laser discs, honey, you remember those old-fashioned things? Now we got da-da-da. And what's it going to be, gang? What's it going to be? I'll tell you one thing that still seems to persist. I've been waiting for years for it to change. And when I was a little kid, I remember I used to look at cars. And I'd look at a car and I'd say, whoa, that car there, they can't design a more beautiful car than that. The designer types are at the top. That Model T, by golly. No, not quite. Okay. But there's one thing about the car I always wanted to see change. That's the windshield wiper. How do you get the rain off your windshield? Choom, 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 choom. There's got to be a better way than that. And I've been waiting and waiting and waiting to see what is going to get the rain off the window. And when you see these great big 747s come in, or you see the space shuttle come in, do you know how the space shuttle gets its rain off the windows, gang? Choom, 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 choom. They still have the same kind of windshield wipers. Isn't that something? Someday, someone's going to come up with something that's going to make the windshield wiper obsolete. And they will say, oh, remember they used to get the rain off the window with the windshield wipers? They don't do that now. Now they have The one who finds out going to be rich. What is it, gang? This is your challenge. Class project. Think of a device that's better than a rubber windshield wiper, okay? I've been watching for years for it to come. Hasn't come yet. I wanted to talk about like the Doppler effect and the sonic boom and shock waves and bow waves. But we don't have enough time now. We'll do that next time. Okay, gang? Catch you then.